Hi everyone, and welcome to another edition of Additive Manufacturing. My name is Reda Zaki, and I'm super excited to go along this journey of sharing with you some knowledge and latest technologies from and for the additive manufacturing industry. As I promised you about a week ago, this video is going to introduce you to design for additive manufacturing, or DFAM for short. But before we start, I'd like to say that I haven't been involved before in an actual DFAM industrial project. With that being said, even though I tried my best to gather information from most relevant sources, please correct me in the comments if I misstated anything or if further clarification is needed. So yeah, let's get started. So here's what I'm suggesting as a structure for this topic. Yeah, let's follow Simon Sinek's golden circle and start with the why. Why do we need DFAM? Why is it important? Then obviously we're going to try to define DFAM, and finally learn how can we design for additive manufacturing and talk about some of the tools and methods available out there. Okay, so why to design for additive manufacturing? Or on the other way around, what happens if we don't design for additive manufacturing? In few words, that printed part, if not designed for additive manufacturing, may end up quite expensive compared to most other conventional technologies. After all, let's not forget that additive manufacturing is an expensive manufacturing technology that's mainly due to the slow additive building process. But this is not always the case. Additive manufacturing can be cost-effective when it comes to the production of geometrically complex parts that are almost impossible to manufacture using the conventional subtractive techniques. Not only that, when a given design or a part design is carefully optimized and engineered, then the outcome could be quite positive, not only economically but also from the functional and performance aspects. And this brings us to the question, should we use additive manufacturing exclusively to manufacture any part we want? And the answer, of course, is no. And additive manufacturing will never completely replace some of the other conventional ways of manufacturing things. However, when the complexity of a part reaches a point where it is just impossible to manufacture conventionally, that's when additive manufacturing could be extremely beneficial. Therefore, optimizing or designing for additive manufacturing contributes and leads to success by adding more value and reducing costs of the printed parts. It can also yield benefits such as a reduction in material use and consolidation of several parts into only one. So what do we mean exactly by designing for additive manufacturing? And where does it come from? So you might have by now already understood that DFAM, or designing for additive manufacturing, is when designers seek to design a product that fully takes advantage of the unique capabilities of additive manufacturing. Personally, DFAM kind of reminds me of the saying, think twice before you speak. Here in this context though, it'd be more like design twice before you hit the print button. Basically, design for additive manufacturing is a term originating from the design for manufacturing, or DFM, which means designing a product that is relatively easy to manufacture. Therefore, DFAM is simply a DFM category dealing specifically with parts manufactured through AM. In a recent review published in Rapid Prototyping Journal, Swedish scientists suggested to classify the DFAM process into three categories, namely system design, parts design, and process design, where these categories should be seen as chronological steps with formulated goals for each step. It is important to note here that parts design and process design are directly connected, as they both have a profound impact on each other, so they should never be considered in isolation. To conclude this section, experts in DFAM seek to fully understand the interplay between the parts application, production, and material requirements in order to come up with a great solution for a specific scenario of parts design, AM process, and application. What you see here is a hydraulic manifold for the Swedish Atlas Copco mining equipment. The version on the left is conventionally machined, and it has 12 nozzles that must be installed individually. The version on the right was redesigned for and produced by Additive Manufacturing at the Creative Design and Additive Manufacturing Lab in Auckland, New Zealand. It is amazing how this new version has drastically reduced weight by 91% and consolidated 13 parts into one, thus resulting in lower assembly cost and increased performance by eliminating any potential leakage points. So how can we achieve such fascinating results through DFAM? Well, there is no prescribed straightforward way to DFAM, to design for additive manufacturing. As a matter of fact, only a few rules of design for additive manufacturing can universally be applied to all geometries, materials, additive manufacturing technologies, and parts. It depends, and that's the #1 rule of design for additive manufacturing, according to the world-renowned DFAM expert, Professor Olaf Diegel. I won't be covering each of these rules, but if you're interested to know more, then I really recommend this book, A Practical Guide to Design for Additive Manufacturing. There are a few optimization strategies out there that allow you to reduce the weight of a part while maintaining its structural integrity and thus increasing the strength to weight ratio. The three major ones are topology optimization, generative design, and latticing, or lattice structures. When performing topology optimization, your goal is to remove as much material as possible from a part while maintaining sufficient mechanical properties. What generative design allows you to do is generating hundreds or thousands of part design options based on input parameters you give to the software. And finally, latticing or lattice structures, which are bio-inspired configurations, allow you to create and repeat unit cells composed of webs with honeycomb or random patterns. Now, to choose the right optimization strategy, we need to fully understand how and where the part will be used. For example, there is a strong focus on topology optimization and generative design for aerospace and aviation mission-critical parts. And the reason behind this is that those structures generated using these two techniques can be relatively easy to inspect and detect surface cracks. On the other hand, this is much more complicated with lattices due to their internal sections. Hence, their use in the medical field, since the parts or implants are relatively set in place. To end this video, I'd like to read these words of advice from Professor Diegel to engineers and designers wanting to add value with additive manufacturing. Because additive manufacturing can force you to think in different ways and allows you to realize complex shapes that could not otherwise be produced, be daring in your designs. Try new ideas just to see if they work. People often say that for entrepreneurship and innovation, it is important to fail fast and fail often. With additive manufacturing, we now have the ability to fail extra fast and extra often. And that's a good thing. Thank you for watching.